Hi, welcome to our presentation. We will present our project titled Avionic System Design for an Unmanned Surface Vehicle developed within the scope of EEE492 Engineering Design 2. Our team aims to design a reliable, modular, and safety-oriented avionic system suitable maritime vehicles. Our team consists of two members. I am Bahadır Mertemelatan, the team leader and software design engineer. My teammate Atakan Saydam worked as a hardware design engineer. In addition, we collaborated with students from different engineering disciplines, which I explain later. Unmanned surface vehicles operate in highly dynamic and unpredictable maritime environments. Therefore, a reliable and flexible avionics system is essential. Our system needs to support real-time sensor fusion using GPS, IMU, and camera, provide robust communication with adjustable frequencies, and allow easy maintenance through a modular design. Most importantly, safety is critical. The system must include emergency stop, remote shutdown, and seamless switching between autonomous and RC modes, especially during communication loss or manual intervention. Existing USV systems face several limitations. First, real-time switching between autonomous and RC modes is often unreliable. Second, electromagnetic interference and noise generated by high-powered marine motors degrade sensor accuracy and control stability. Finally, many commercial controllers are not designed for high-power systems, AI integration, and multi-sensor fusion simultaneously. Our goal was to design a noise-resilient, integrated, and modular avionics system that overcomes this issue. We defined clear engineering requirements for our system. The navigation subsystem must provide at least 80% accuracy in heading and orientation. The system must support real-time RC autonomous mode switching. Autonomous navigation performance should achieve 70% route tracking accuracy. In terms of endurance, the system must operate for a minimum of 2 hours while keeping the total avionics weight below 1.5 kilograms. To meet these requirements, we designed a custom avionics architecture combining high-level AI processing with low-level real-time control. The system separates decision-making and actuation tasks, improving reliability, scalability, and fault tolerance.
Hi, it's Atakan. I will present our hardware system. You can see our hardware design parts here. This diagram shows the power distribution of the system. The 12-volt input directly drives the vehicle contactor, while the 24-volt input is converted into three different voltage levels for use. The power system is divided into isolated and non-isolated sections to protect the sensors and the microcontroller. You can see how we carry out the power distribution from this diagram. This diagram shows the importance of battery voltage measurement for mission time and operations. For our isolated system, voltage measurement requires a careful engineering. As seen in the Altium schematic, the battery voltage is first reduced to very low values using a voltage divider circuit. Then it's converted to a 0 to 3.3 volt range by an isolated amplifier. A 3.3 volt Zener diode is placed at the output for high voltage protection. Finally, the signal is sent to our analog digital converter module and then transmitted to the microcontroller. GPS sensor has a critical application because we implemented RF positioning directly on the board. We received assistance from professional RF engineers for the implementation. In our test, the designed GPS units connected to 19 satellites and performed position measurement with 1 meter precision. For the IMU sensor, both an evaluation board and surface mount methods were used. The BN0055 IMU is a very difficult sensor to assemble because of its bottom pad soldering structure. Therefore, an evaluation board interface was placed next to the design to allow for easy replacement in case of a sensor failure in the field. Since the 4.1 microcontroller is placed at the heart of the system, it is a very powerful microprocessor that can reach speeds of 600 MHz using a processor like the Tinzi 4.1 is important for high capacity and fast operations. The system offers multiple communication options. User can choose between LoRa or XBee modules to communicate with the RC control and ground station. In this photo, you can see the fully manufactured and assembled version of our board. The connections and cabling are shown as they appear in the final setup. In this photo, you can see the 3D view of our board design in Altium Designer. In this slide, design images exported from Altium Designer are shown. The image on the left displays the signal routing, while the image on the right indicates the power and ground planes.
First, all sensors such as GPS, IMU, and camera are initialized. Then position and orientation data are continuously acquired. Sensor data are filtered, logged to an SD card, and transmitted to the ground station. At the decision level, the Jetson Javier computes to target heading and speed. At the control level, the TNZ 4.1 calculates actual heading and speed values. The system then computes heading and speed errors. These error values are processed through a PID control block. Finally, PWM signals are generated to control motor thrust via ACS and rudder angle via a servo, ensuring stable and responsive motion control. To validate our design, we performed unit test, module test, functional test, and integration test. Each subsystem was tested individually before full system integration to ensure reliability and correct operation. At this stage, we tested the subsystem one by one. The control system can read data from IMU, GNSS, and RF modules and generate PWM signals. The ECS, ESC, and motors Motors respond correctly to these PWM signals. We also verified that the commands from the RC remote control are received correctly and converted into PWM. In this part, we test all power distributed across the vehicle to ensure it reaches each component at the required voltage levels. Measurements are taken and any errors are corrected. Finally, optimization is performed on the adjustable converters to ensure peak performance. In this test, we tested the system in an environment close to real operating conditions. Based on the data received from the sensors, the control algorithm drives the motors correctly. The motors respond in terms of speed and direction according to the incoming PWM values. Commands from the RC are received via RF and transmitted to the motors. At this stage, we tested the entire system in an integrated manner. The sensors, control units, RF communication, and motor drivers are working together seamlessly. No problems were observed in power levels or communication lines. Telemetry data can be monitored in real time from the ground station. This test shows that the system is ready for field.
This slide shows the cost analysis with the price of each material used listed individually. The costs for passive components and integrated circuits are based on approximate price, and the total amount is over the 100,000 Turkish liras. Since our product is in the field of maritime electronics, our target customers are the Turkish Naval Force, the Coast Guard Command, and Ministry of National Defense and ASFAT for product integration. Developed with entirely local engineering, this avionics system addressing the technological gap in the maritime and defense sector with providing a sustainable solutions through its field durability and commercializing potential. Consequently, it aims to commercialize with the defense industry.
Safety was a core design priority. The system supports remote shutdown, allowing the operators to stop the vehicle instantly. In case of communication loss or critical faults, the system enters a fail-safe mode. Additionally, a contactor-based power isolation system safely disconnects high power lines when necessary.
In this slide, you can see our collaborations. We would like to thank the Gazi University Technofest Coordination Office for their great efforts during the customs clearance stage of our PCB. I would like to thank Mohammed Said Gönül for his expertise in computer engineering, specifically for designing the RC system, and Ahmet Berkay Yılmaz for his vital contributions to manufacturing engineering and the structural assembly of the vehicle.
In conclusion, we successfully developed a modular and reliable USV avionics board capable of operating in dynamic maritime environments. The system enables seamless switching between autonomous and RC modes, integrates multi-sensor fusion, and includes strong safety mechanisms. With its flexible communication infrastructure and ease of maintenance, this avionics solution is suitable for both professional mission-oriented applications and hobby-level USV usage. Thank you for listening.